All right, so you just watched the videos that was all about structures, right? And how nature uses structures to create function, right? And of course, we're all around function, and we're all around different structures. And I think that one way to start thinking about this is to think about the different materials that we have, right? Often when we think about materials, we give it a certain set of qualities that we think it might have, right? So if we're thinking about any kind of plastic or rubber, right, we always think of that as being like soft and malleable, right? We can move it easily around. But of course, that's not necessarily true, right? I mean, we have a lot of plastics that are very hard, right? I mean, the case of your phone and all those kind of things, that's all plastic, right? Maybe some of the casing around your laptop, right? That's all plastic. Of course, my glasses are plastic as well, right? I mean, it's all very hard things, right? So that's one way to think about it. The same thing if we think about rocks, right? We think of rocks as being these, durable things that are going to be there forever. But if we look around that rock, right, there's a whole bunch of sand there. Now, sand doesn't necessarily come from that specific rock because it's sitting on the ocean. But of course, all of our rocks slowly but surely get ground into sand, right? And then we think about the eggshell, right? Something that's very in a way very brittle. It's easy to crack an egg, right? But considering how thin its wall is, it's actually quite strong. And we'll actually be looking at how strong eggs are next week, because as you hopefully have figured out, next week is engineering week. And so we're gonna repeat the grand success of our egg toss from last semester, from last year. And so basically we'll have you get together in teams, pack eggs in some materials that we give you, and then we'll see who can drop them from the top of the stairs without cracking them. I think last year we had two teams that actually got the egg down there without breaking it. But we'll talk about that more. All right, so these are kind of different materials, and we've talked about materials in the past. But today we're not really talking about materials. We're going to talk about structures. Right. And so one thing that is kind of similar to materials that we think of something like a piece of paper. Pull out my prop here, right? Just a regular piece of paper. Move my camera just a little bit here. I'll move it back in a second. Just need to be able to see my table. Right. So if I think about my little piece of paper here, it's not very, doesn't do very much, doesn't stand up, right? If I wanted to support something, right, I can't put my folder on here, it's just gonna fall apart, right? It's not very good at doing that. But if I take that same sheet of paper, or it's a different sheet, but still just a regular piece of paper, there's nothing there, right? If I just fold it together, make a little tube out of it, and now let's hope it actually works. It does, right? So just by changing the configuration of my paper, right, I can get it to actually be strong enough to hold that paper folder up, right? Obviously, you could say it's not a very heavy folder and all that kind of stuff, but still, right, I can simply change what my configuration is with the same material, and I can come up with something that is much stronger. And of course, we've take advantage of that, right? We build all kinds of fancy structures, not by creating a big chunk of something, right? But if you think about, and I'm not going to ask what these are because we played that game during the seminar already, right? But you think about the Hancock Tower, right? It's not one big solid brick or something, right? It's a steel building with concrete in it, right? So it's has all these different structures similar to the Golden Gate Bridge, right, which is also steel and concrete. And we've been doing that for a long time, right? We've understood how structures work. And if you look at these three pictures, what's very like the common element in them are these arches, right? We have all these arches because we've understood that arches are very strong, right? These rounded shapes that we have. We don't need to put all this material in here. We can just kind of do these arches, and we can see them like the Roman times and then in medieval times, right? So it's really quite interesting that we came up with that. So we're very good at building structures. Of course, our structures don't always work, right? Sometimes they fail, or quite obviously, quite often they fail. That can be kind of a slow failure, like the Tower of Pisa, which they noticed that as they were building it, that it was leaning, so they kind of tried to adjust a little bit, but it didn't work. But it can also be kind of more sudden failures, like this bridge here, where the bridge failed, there's a little balcony that crashed onto somebody's car, and of course, I would assume most of you have seen this beautiful view of a cracked screen on their phone, right? I'm not sure. My kids are going through cracked screens like there's no tomorrow. It's quite. They're supporting an entire industry, right? And then we've already talked about this building that fell over. And actually, if you want to see something really, really, I guess you can say almost spooky in a way, is that so in China they've overbuilt their residential buildings, right? Quite the opposite to what's happening in Costa Rica and the US, where there's not enough housing. They've actually built too many of these kind of mid-luxury buildings, and so you can find these videos online where there's like basically like here, like you have all these big buildings that are all being blown to pieces, right? They're just demolishing them right before they were even used for anything, because there's too much stock and it's driving down the prices. But nonetheless, right, the idea is that we have all these failures, and of course we want to understand how these failures happen, because that helps us to design stuff to avoid failure, right? So if we know why this glass breaks, right, on the phone, then we might be able to design a glass that doesn't break. Now, to do that, we have to understand a little bit about the mechanics of my objects. And so one little thing here that I like to show, right, is this little piece almost looks as if it's a sponge from the kitchen, right? So if I take this sponge right here, it's just sitting by itself, and I kind of draw these rectangles on it to make it a little easier to see. Now, if I bend that, then you can see that kind of the top ones at the top end of this, the sponge is being pushed together. On the bottom end, it is being pulled apart, right? And we talked about this already when we talked about the idea of concrete, right? That whenever I have a beam, it gets pushed very hard at the top and stretched at the bottom. However, if we look at kind of the center of this, that doesn't really change very much. It's not being stretched, it's not being pushed. So there's not a whole lot of what we call stress in here, right? And I think many of you have taken Physics 1 already, or maybe you're taking physics, or you can't take Physics 1 right now because we're teaching Physics 2. But if you've taken Physics 1 already, right, you've learned about the concept of a stress, right, which is a force divided by an area, right? So you can say up here, where everything's being pushed together, we have a compressive stress, right? Something is being pushed together. At the bottom, we have a tensional stress, right? Stuff is being pulled apart. In the middle, nothing's happening, right? It's basically just there. There's nothing in there that we need to do. And so based on that idea, we developed what is called the I-beam, right? Which has a big piece of metal at the top, a big piece of metal in the middle, and then a connection between those two. And the idea, again, is that if I'm putting any kind of weight, or even the weight of the beam itself, on this beam, then there's going to be a lot of compressive stresses at the very top, and a lot of very tension stresses at the bottom, but not much in the middle. So I don't need to put all this material in here. I can just take kind of all this material out, right? In a way, you can think it like this, right? We're taking the material from here and moving it up to where the stresses actually are, right? That means we're using a lot less material, which is of course great, right? And not only is it good because we're spending less money, we can also make these beams smaller then, because they don't have to support their own weight, right? Like the weight that this beam supports is less. And if this is a set of beams on the 3rd floor and there's 10 more floors above it, of course, if all those beams are lighter up there, then there's less stress acting down on my beam, right? So overall, I can use a lot less material in building. And so, of course, when we started designing these, we're very proud of ourselves. We built this great I-beams, and of course, nature has been doing this forever and ever, right? So in nature, it's not so much an I-beam. In nature, we usually see tubes. There's a lot of tubular structures out there in nature. And the reason is that, of course, for my I-beam, I know the forces are going to be acting down like that on it. On that little flower stem, right, the wind can come from here, it can come from there, from everywhere. So I basically have to have a structure that's stable in all directions, and that is a tube. And if you walk around and look at those, look at the bamboo that you see all around Escazú, right? Then you can see how strong those are, right? I mean, those bamboo trees can get very, very, very tall, right? So it's quite amazing what you can see, right? So that's one part, right? So we're kind of trying to understand or we have an idea now how kind of a force goes through my material. Now, the other very important thing that you have to think about is when they fail, like what happens when they fail. It turns out that cracks are quite important when it comes to failure of most materials. And again, if you're an industrial, then you'll take material science and you'll have, like, 2 or 3 weeks worth of material that's just about cracks and failure there. And of course, most of the cracks we'll see are small, like this in the sidewalk here, but you can think about this as a crack too, although it's a little bit of a stretch because I think this is more like looks more like fluvial valley than an actual crack, right? Places where you can see larger cracks would be in places, if you want to look to the natural world, would be where like the ocean plates kind of pulled apart, right? You'll see that would be kind of more of an actual crack, not so much a fluvial structure. Now, these cracks can be very important, and where they originate can be very interesting. And so here are 2 examples that are relatively famous in the world of material science. And on the left, we have a ship that's cracked in half, which is never good. And then this plane right here is one of the early jet planes that we had. And this one looks all good, but not all of them did as well, right? So we'll start with a ship here. So this ship here is one of the ships that was a whole series of ships that was built during the Second World War called a Liberty ship. And so these ships were built, obviously, in docks. And then when they went into the water, they started forming these big cracks. And fortunately, most of them formed those cracks while they're still in the harbor, not while they're in the middle of the Atlantic. And the reason why they form these cracks basically is that there's certain types of metals, when there's a temperature change, they go from a metal like we understand metals that are very strong and very durable, or you can kind of hammer around on steel for a while. But if in the wrong temperatures, they go from something that's very, very strong to something that's very brittle. So basically more to something that acts like glass or something, right? When you hit it, it just kind of breaks into pieces. So that's what happened to these Liberty ships. And these planes here look very sleek and everything. But they kept on falling apart when they're in the air, right? Which is obviously not a good thing because, if your plane rips open in the middle of the flight, then that's not so great for the passengers. Now, when people looked at this in more detail, for the Liberty ships, they noticed that for the cracks, these big cracks that then kind of broke the ship apart, they noticed that they all started at the corners of these kind of like, shafts where you load the cargo into the boats, right? On a corner here. And for the planes, the cracks all happened at these intersections between the window and the rest of the body. And so considering this, people realized that, or already knew that, but kind of saw this in action. And that is that whenever you have any kind of a crack, or any kind of a notch, if you want to be a little more technical about it, right? That at the tip of that notch, of that crack, the stresses get concentrated, right? So if I have a nice big area here, and I'm pulling here and I'm pulling there, then the stresses are going to be the same all over the place, except at the tip of this crack where it's going to be a lot higher. And there's equations how you get it, and it depends on how pointy the crack is, right? So the sharper this crack is, kind of the more narrow it is, the stronger the stress concentration is going to be, right? So we know that anytime we have a notch somewhere, we're in trouble. And so it turns out that a right corner is a notch, right? It's doesn't have a very, very fine tip, but it still is a notch. And so we see in many things that we have cracks kind of form at the edges, at the corners of these rectangular shapes, right? So this is just the sidewalk, right, is cracked along where the corners are. That's just because the stresses in the concrete, right? For the concrete, this is kind of a cut right here, right? So the stresses are going to be the highest there. You can walk around, maybe not near your neighborhood because the houses are too far set back and the walls around them are too high. But right, if you walk through like an urban neighborhood, you'll often see that there's cracks that are forming right at the corners of windows. And of course, this one here is after an earthquake, and you can see like, that the cracks all started forming at the corners of the windows, right? They don't just crack in the middle. I mean, they cracked all the way across, but the original cracks all happened there, right? And that basically means that happened because the stresses there were the highest, and that's where it fails first. Now, unfortunately for us, we can't see stress, right? We can't, there's no way for us to experience stress. I mean, obviously we all experience stress, but from a material standpoint, we don't interact with it, right? It's not like temperature that's hot or a color or something like that we can see. So that makes stress difficult to deal with. However, every now and then, for certain materials, we actually can see stress. So if you're at the airport and sometimes you see that the windows of an airplane have these weird colors, or if you're sitting in the window of the little windows in there, they often have these colors, and that's just because they're polarized, and so you can actually see these. So now, if you want to do, we'll get to that in a minute, but if you have this the clear plastic kind of that's around, not the soft one that's around fruit, but like the little containers. Kind of, if you take one of those and you put on polarized sunglasses and you hold it up against the screen and you move it around, you can see the stresses in there too. So you should try it, but it has to be polarized sunglasses. It's non-polarized sunglasses. It doesn't work because your screen is polarized and your glasses are polarized. So it's a nice little side project you can do. All right, so that was technology. How about nature? How does nature does it, right? You don't see sharp corners in nature. Everything in nature is nice and round, right? I mean, the horns of the sheep might be like, the tip might be a sharp corner, but the main part of it is nice and round, right? So we remember that we saw, right? They like to bang their heads together with the horns, and so there's going to be a lot of stress on them, and so they want to make sure there's no notches to crack it, right? Same with an egg, is nice and round, right? So every time I push, forces are going to be kind of flowing around it, and our heads too, right? Our skulls are also around, and we'll talk about why we have these kind of predefined cracks in our skull in a little bit. Now, how do we do stuff? Well, we don't like to do stuff at round angles. We tend to have sharp angles. Now, one thing that we can do with that we do a lot is that we use what's called a quarter circle fillet. So instead of having a right angle like it would be here, we kind of are filling it in with a quarter circle. Now, it's not always a quarter circle. Sometimes it's more like inverted or something, but it's basically, we do that so that there's less stress concentration in these areas, right? If I just had this going straight down and then straight over, I'd have a very sharp corner there, and the sharper that corner is, the more stress concentration is going to be. If I round it out like this, then there's going to be a lot less stress there. That's why when you see I-beams or anything like this, right, they're never sharp, or usually not sharp corners. They're always kind of rounded out, because that means we reduce the amount of stress that's happening there. Now, it's a great idea, but doesn't always work, right? So this is just somebody's old car, and you can see that even though that was kind of a rounded off area, it's still where it broke. And if you look at this little dispenser, this little tape dispenser, right? So this would be looking at it like in front of a computer screen and through your sunglasses, or you kind of see where the stresses are, and you can see the highest stresses are still down here in kind of the curved shape. And here we have a manhole cover in Chicago, and it also, like, although it's not sharp corners, the concrete still broke along the edges of this manhole cover. So it's better, but maybe not perfect. All right, back to nature. How does nature do all this, right? So we see this beautiful big tree, right? And of course, especially, well, here the last couple of days, Costa Rica this time of year too, right? We get a lot of wind. So why don't we see more trees falling over, right? There's a lot of wind blowing into this tree, so there's going to be a lot of stress at the bottom of this tree, right? Because it looks like it's a huge sail up here, right? And not a whole lot of tree to hold it in place, right? So we have all this wind. So what happens? Well, the first thing that happens is that the leaves actually are designed to fold up as the wind gets bigger and bigger, right? So we have that very like a regular looking leaf up here with no wind, and then we kind of keep on increasing the wind, and instead of just staying the same shape and kind of flopping around and being a big resistance, as the wind goes, it kind of pushes on it, it naturally folds together, right? So it's not not something that the leaf does intentionally. It doesn't fold itself up. It's just as the wind gets stronger and stronger, the forces are getting stronger and stronger. The way it folds is folding into that nice shape, and so it gets really nice and aerodynamic. And the same with these leaves over here, right? So instead of kind of sticking out one by one, they kind of group together and become nice and aerodynamic, which of course means that if there's a lot of wind, then the force that is acting on my tree is less because there's less wind resistance, right? Same idea of having my folder fall like this versus my folder fall like this, right? Very little resistance if it's coming kind of straight at you, but quite a bit of resistance if it's going like that. Idea of a parachute. Well, you can say that as well. All right, so that's one thing we can say. Winds are staying up because they're reducing the load on the tree through the leaves. But that's not always the case, right? Here, this tree is being attacked by not a big windstorm, and even doesn't have all that many leaves on it, right? But there's a car that ran into it, right? And so now, it's not that big of a tree, to be quite honest, right? And it kind of folded up that car quite significantly, right? I hope the people that were in that car survived, right? I mean, this is a fairly serious crash that we see here. Like the whole roof fell up. Right? How fast this person was going in the middle of the city, I have no idea, but certainly faster than they should be. But the important thing here is that tree looks almost unharmed, right? I'm pretty sure that the bark on that side is ripped off and all that kind of stuff, but the overall structure of this tree is there. It didn't just fold over. And so why is that the case? Well, there's one big reason for that, for the trees being so strong against the kind of being broken in half, is we can see that when we kind of saw through one, right? So I think we've all heard about the concept of year rings, right? On a tree, where there's consecutive kind of, like in the spring there's one type of wood, and in the fall there's a different type of wood that's being put down, right? That the tree grows. And so you can see that, right? We can see these darker areas. Those are the fall wood, and the light wood here, that's kind of the spring and summer wood. And the difference that the reason we have this difference is that in the spring, the tree has lots and lots of water, lots and lots of nutrients, so it's building out, it's expanding very quickly, right? So it's basically creating these, like it's all cellulose, right? So there are all these tubes, and it's creating them as big as it can to, grow as fast as it possibly can. In the summer, there's much less water, right? So like these tubes become smaller and smaller and smaller, right? So there's basically a sequence of different densities of wood that the tree produces as it's growing wider and wider and wider. So if we look at that in a lot of detail, right, then basically we have this spring wood, big wide chambers, and then we have the summer wood with its smaller chambers. Now the cool thing is that the wood that we have with the big chambers, that wood is quite flexible. It can move. The very dense wood from the summer is very strong. So basically what nature has created is a composite material, where it has a soft material together with a very strong material, right? So that means that this overall, this tree can flex, it can move around, but it's also very strong, right? If it were only the hardwood, right, then it would break off because it can't, right? If a car runs into it, it needs to move a little bit and then come back. If it's just very rigid, it's going to break. But if it's a little bit flexible, it can actually withstand that. If it were only the soft material, right, it would just flop over all the time, right? So you have to have these two, and the combination that they create is this great composite material. And actually, we do that all the time. We see that in all kinds of other stuff. Again, if you want to think about the materials class, you'll learn about why different metals have different strengths, and different ways of creating metal have different strength for the exact same reason for this, where they have different types of material, a little stronger and a little more rigid, but you'll get there. Another thing that we see in wood is, again, this is just zooming in a little bit farther, is we have all these very, very, very many little channels here, right? And so what that means is that if I get a failure in one of my little tubes here, right, that were laid down as wood, if one of them breaks, that's okay because there's 10 around it, right? So it's a very, very redundant type of system. So that helps with the strength. And then if we zoom in even stronger, right? If we zoom in into one of those or a couple of those pipes, then we'll see that they're actually completely separated, right? So this would be one channel. Here's another one. There's another one. You can see there's clear distinctions between them, right? It's not just one big piece of material. There's a break here. This is not because they've been disrupted. This is on purpose, right? And the reason is that, again, something you'll learn in materials is that fractures don't want to go across boundaries, right? So if a fracture comes to a boundary, it will kind of go along the boundary instead of going across the boundary. And there's all kinds of reasons for it, free energy at surfaces and all that kind of stuff. But that means that if for some reason this tube here gets a crack and starts to fracture, it doesn't just fracture to the next one and the next one and the next one and the next one, the whole thing just collapses. No, it actually stops there, right? So only one of them gets destroyed and the rest can stay the same. And so we do very similar things, right? So if you think about this as a sidewalk, right, you can see there's a right angle here. That right angle formed a crack, but that crack didn't just keep on going. It went to this next little kind of border within the cement, and then it ended there. That's why we have our cement pieces are always bordered off, right? It's not, if you think about a sidewalk, we could just have one long concrete thing, right? But no, we put these borders in so that if a crack forms, it will go to that border. And then over here, we have a big steel cable, right? If you think about a steel cable, it's not just one big piece of steel that goes along. It's a whole bunch of smaller cables that are all rolled together, right? And so that means that if one of these cables breaks, not the whole cable's breaking, just one of them, right? And so because it's not a huge thing, the crack is not going to be able to form and go all the way through. It's just going to go through one of those cables. That cable breaks, and we hope that the bridge was designed in a way that a couple of these smaller pieces can fail before the entire bridge fails. Now, that doesn't mean that we don't want to go in and look at the bridge once a couple of these fail, right? We probably want to replace them then. But nonetheless, it's a lot better than having the entire bridge fail. Now, I said we're going to get back to the little fractures that we have in our skulls, and these are normal, right? This is not because somebody hit this person over the head, although it seems they smacked them in the teeth because half the teeth are missing. But the same thing happens in our skulls, right? So if we have these kind of pre-designed fractures in there, so that if for some reason a fracture does occur, it will not continue through the entire skull and make us vulnerable to, or make our brains vulnerable to injury. All right, that was a lot of talking. Are there any questions? So take 2 seconds and look around where you're sitting. Like, on your desk, look at your windows, look at your chair, right? Most of what you see, you'll notice, is more or less sharp corners, right? There's very few things that we build that are round. And the main reason, why do you think we like to build stuff at right edges, at right corners?
Cost?
Sorry?
Cost? Like price?
Cost, yes, but why is it cheaper to build something at a right angle than at a curve?
Because it's simpler.
It's much easier, exactly, right? It's really easy to create a right angle, right? When you're drawing something, right, it's always nice and easy to draw a right angle. Drawing a nice curve, much more difficult, right? And going back to my industrial engineers, when you take engineering graphics, you will learn how difficult it is to draw a nice round circle. You can ask Gloriana. She's already been able to practice that, right? So, but that's why we do all these. And sometimes we just have to build our structures stronger than they need to be, because we have these right angles. And there's a famous architect in Europe. Well, he's a painter, but he also created a couple of houses, and he's very well known for like his painting is always like, the shapes are all very strange, a little bit like Dali, but not him. And so he also decided to build kind of a housing complex, right, like a kind of an apartment building, but in his same style. So everything was kind of rounded off, and there were no corners. And the construction workers went nuts. Right, it was like impossible to build because there's like no sharp corners to do anything. And all the bricks had to be set in like weird ways. And then the people who moved in afterwards also did not like it at all because there's no straight walls to put a closet against. Right, so it was sometimes there's good reason to do this kind of stuff. All right, let's move on to some more nature, and that is we're going to talk about trees. Right, so we already talked about trees. Like the internal part is very strong. Right, we talked about the ideas. But that's not the only thing that's keeping the trees standing up. If you think about a tree again, right? If the wind is blowing against it, there's all the weight of the tree going down on it. There's going to be a lot of stresses at where the tree goes into the ground, because that's basically, at least from this view, right? It's a fairly sharp angle there. And so people started looking at this, and this is one of the people who kind of came up with the idea to understand why trees are so strong. And so if we zoom in a little bit, right, we can say like, well, this is just a quarter circle. That's just another fillet like we had before. But if we do that, it's not really the case, right? It comes out quite far. Right? This is a lot slimmer than a quarter fillet would be, which is good because it means less material. And so the researchers went around and kind of measured out what these curves are. And they call it a tree curve, and you can say like, well, that's all fine and good. You can call your curve whatever you want to, but it turns out that this is actually universal. So this is not just a curve, is that trees, when they go like, where the roots come out, have this kind of tree curve. And you can find that all over the place, right? Now, the trees with those big roots that are up, like they're kind of, the roots are all exposed, they're kind of the big walls of roots coming out, that's a little bit different because the way that they anchor themselves into the ground is a little different. But still, if you go a little higher up, you'll notice where they start is on the same tree curve. And so we can find this tree curve all over the place. And it's not just a theoretical curve, we can actually reconstruct what it looks mathematically, right? So if we start with the bottom of it is a 45-degree angle, then we go halfway up and draw another line that's half of 45 degrees, and we draw it up until it kind of hits that same area, and then we keep on doing that, right? We do 11 to 25 again at the halfway point, and then we kind of keep on going until we have kind of it becomes a straight line, right? So this is the tree, the tree curve, and it turns out this tree curve is actually very good at distributing stress, right? So this is kind of the little home project that you can do if you want, right? This is kind of the type of plastic that goes around like food containers and those kind of things. If you cut a very sharp corner, then you can see there's a lot of stresses here, right? You see like the very strong coloring in there, not very many stresses everywhere else, right? So this means it's very easy to create a crack here and have the whole thing fail. If we round it off, it's much better, right? So the stresses are distributed over a larger area, but there's still not very many around it. Most of them are there. Now, if we do this with a tree curve, then we can see that stresses are kind of distributed throughout the entire thing, which is what we want to have, because the more stresses we have distributed throughout this thing, right, we have the material there. And actually, in this shape here, the stresses are fairly low compared to the rest of our system. So that's great. That's how trees evolved, right? And it turns out that if you do some analysis, some mechanical analysis, that the stresses are reduced by 57% compared to even a quarter fillet, right? So that's quite amazing how nature evolved to grow like this. And again, you can go through the forest, you can take out your little measuring stick somehow, and you can see that they all follow this shape. Obviously, it's not always exact, right? But this overall shape is all the same. See very few trees that go straight into the ground unless we did something to those trees, right? So of course, if I have a tree like this and then I dump soil up to here, right, then we're not going to see this tree curve anymore. Now, trees are not the only ones who do this. You can find these type of kind of drawn out kind of corners everywhere in nature, right? So I guess this is still technically a tree because it's a leaf, right? We can kind of see that here because the leaf doesn't want to rip. This is a moose antler because the person that I worked on this with is from Montana, so there's a lot of moose around. We can see it between our fingers, right? Kind of a round shape everywhere there. And we can, even if we zoom in, we can see it on neurons, right? Kind of the ways that our nerves work, right? They all have these nice rounded out corners. Now, of course, in technology, we don't have very many of those, right? As I pointed out around your room, we have a lot of these little kind of notches and sharp corners everywhere, right? Everywhere on this bridge, in this car, right? All the corners here where the glass is. Many, and then in a screw, right? Obviously, like each of these kind of the bottoms and the tops here are very sharp corners, so that's where they'll fail first. And actually, if you look very carefully at these screws, you'll see that their tops are not actually sharp at all because they're flattened off. Because at some point, people realize that if they have these sharp edges, first of all, people cut their fingers all the time when they work with screws, which is not great, but also they fail faster, right? So it's softened up or it's flattened up there, and it's also flattened at the bottom. And that's another thing that we'll talk about in engineering graphics. But we've learned, right? So we can make differences. We can actually use nice curves, right? So this is the wingtip of a plane. This is one of those things that engineers stumbled onto, right? So until 20 years ago, like the wingtips were just flat, right? There was nothing on this. Basically, as if I cut along this line right here, this kind of blue line. But it turns out that if you add this little vertical or almost vertical wingtip, you actually reduce a lot less drag than if there's nothing there. That's just because the way that the air flows and the way the turbulence is created is different with this little tip. And these little tips, I don't remember what the percentage is, but like it increased the amount of or they decreased the amount of fuel that planes needed by a significant amount. That's why you see all the jetliners now have these little tips. If you're getting on any kind of good sized plane that doesn't have those tips, then you might want to step back off because it's going to be a very old plane. But we can see that in bridge construction too, right? So we don't have a flat underside of a bridge, but we have a curve. So that goes back to something that we've known for a very long time. I remember that the Roman structures that we saw at the beginning and the medieval structures all had kind of these arcs everywhere. All right, bringing it back to our trees, right? We can say that one of the reasons why trees are so strong is that basically the strength and the resilience is designed into them at multiple different levels, right? So we have kind of the idea of that the tree curve to create less stress. We have a system that maybe this picture is not the best picture for it, but I mean it has its redundancies, but it also has this kind of mix of very hard and more softer materials. It prevents cracks from forming. And it uses a tube shape that we said is in general a very strong type of structure. But that's not all. Right? We have more for our trees, right? Trees and plants in general are very good at adding material where it's needed most. Right. So if I have where this kind of branch comes in, there's going to be a lot of stresses on this area of the tree if there's weight on this branch. And so this tree has grown to have more material here because that's where the stress is. And it's not only plants that do that, we do that too, right? So our bones do that. You can do imaging and look at bones of people before they went through a large exercise regime, and then weeks and months, if they keep on going with it, then the bone mass actually increases, right? Creates more and more stronger bones because they're being used and there's stresses on them that weren't there before, and so the bone density increases there. So that's creating more mass, but having more mass is not always a good thing, right? So of course, in nature, we always want to be very efficient, so we don't want to run around with a lot of extra mass on us, right? So if you think about this gazelle or whatever that's being chased by the predator, right? It wants to have the least amount of mass so it can move the fastest as possible and wants to be able to basically make very sharp corners and all that kind of stuff, right? The the more mass you have, the more difficult it is to take to get around corners, right? So of course, the gazelles that survive to reproduce are the ones that are a little more lean because they got away from the predator. And so that comes then with the idea of dematerialization, right? How can I take as much material out of my system without compromising the strength of the system, right? So we can think about that for mammals, right? Certainly with our bone structure, right? The thing that's really creating stability for us are our bones, right? Of course, we have to have ligaments and muscles and all that kind of stuff around them to hold them together, but like kind of the strength comes from the bone, right? So we think about like for instance our leg bones, right? We don't have one big leg bone, we have two pieces of leg bone, right? Because that creates the same amount of strength with less mass. And even if we zoom into bones, we can see that a bone is not solid, right? But it's kind of just kind of tangleweed of little pieces of bone as they grow. The good thing is that, of course, once it does that, we can, if we need more, right, we can grow a little bit more bone in it, and we can repair bone as well. But we can take that same idea and use it to design mechanical things, right? This is a skateboard, for instance, right? So I can go through and think about where is it that where I have stresses in my skateboard, right? And so in places where I don't have a huge amount of stress, I don't have to have material, right? I might be able to get away with no material whatsoever, right? So we can do that, and so we can design these kind of skateboards basically that are kind of these weird looking, alien looking type structures where we're concentrating kind of the mass around where we really need it, right? We need it around where our trucks are connected to the board, right? There's going to be a lot of stresses here, of course. We'll need to have some kind of center spine that's strong, and we'll have to have some end pieces that are strong, right? But we can take a lot of material away. Now, we probably still want to cover this all by something so we don't get caught in it, right? But we could cover this with something that's much that's much weaker than the material that's holding it all together, right? So overall, we'd have a weight reduction. And so we have that in well, skateboards. We don't see that very much because the skateboard in the end is not very heavy to start out with, and most of the skateboards are relatively cheap. But we also see that in motorcycles, right? Maybe not quite so much with kind of these organic looking shapes, but if you look at the back here of it, right, we have these big cutouts here and here. We have big cutout, or it's not the back, it's the front. The big cutouts here in the middle. We have a lot of places where there's large cutouts in the middle because we don't need it there, right? It doesn't produce any, doesn't make the system any stronger, and just adds to the weight. We don't want weight, right? If we want to have a fast motorcycle, we want to have it as light as possible so we can accelerate as much as we want to, because of course F is equal to ma. So if I am able to reduce the m and still have the same force, then my a is going to be bigger, right? So it's very simple. Now we can do the same thing with bridges, and I would say that from the very beginning, even a simple bridge like this already does that, right? We're not adding one big wall down here to support the entire deck, right? We're just doing pillar by pillar, but we can go even farther, right? We can go through and create these organic looking structures that reduce where we need to have it, right? You can kind of see it here already, right? This bridge here, I just realized, also has cutouts in the bottom, right? So to make it, because we don't really need a specific amount of or there's not a whole lot of stress there. We could do the same thing in planes, and in a way we already are, right? If you think about the construction of a plane, it's not a big thick layer of aluminum. It's like, you know, we have kind of an inside skeleton and then a very thin sheet of aluminum that sits on the outside. But again, we could go a lot farther, and we could have kind of these very thin structures on top of it. Now, for some people, that might not be such a great idea, because some people are already kind of worried about flying. But if you're not, then just imagine you're sitting in this plane instead of the regular plane. Just look at the great view you would have. Of course, I'd be more interested in if the floor were looking like that, because in the end, when you're flying up in the sky, there's not all that much interesting stuff you can see on the top. But if you don't have a window seat, it'd be really cool to be able to look straight down. All right, so but that's
This type of design has a specific name, right?
could be. Do you know what it is?
I've heard of it because I've seen a lot of it in 3D printing. I'll search for it and I'll let you know if I find it.
I bet, because like if you think about 3D printing, right? If you I mean you know it because you've done a lot of it, but if you look at if you go down into the manufacturing lab and look at some of the pieces that either failed or where we kind of stopped them early, you can see that the inside is not solid, right? But it's kind of a honeycomb structure or something like that, again, to reduce the amount of weight, because we don't have to have a solid brick of something, right? It's often strong enough if we have those honeycombs in there. So that was planes. We can do that with furniture, right? We can have our regular table here. Now, of course, we don't need to have it be so thick, and the legs are probably thicker than they need to anyway. But this is probably more for aesthetics anyway, right? I'm pretty sure that this table from a mechanical standpoint would be horribly over-designed and like, way too thick and way too heavy for what it does, but nonetheless, it looks, at least for some people, it's going to look nice. I'm not sure if that's necessarily my style. But we can kind of use the same concept as we did with the bridges, and we can kind of take out where we think we don't need the material. Then we can come up with these very, very slender, sleek-looking structures, right? They're not as massive as this table, but they're very, very thin and slender, but they're still quite strong. Right? We don't have to worry about them falling apart. Now, one thing where this has been put into practice more or less, this is not never went into series, but Mercedes-Benz built this concept car where they basically thought or used the skeleton of a boxfish. Right? There's these very weird boxy looking fish, and so they took that, and so instead of having the regular structure of a car, they kind of created a structure that was minimized, weight minimized, based on kind of how that fish skeleton looks like, and they could reduce the weight of the car by 1/3. Right, so that's a huge difference. And of course, you can always reduce the weight of the car by putting less and less metal in it. And at some point, you can have a car that's super unsafe. But this car was just as safe as any other car. Right, so it basically did not lose any of its qualities by reducing the amount of material that was there to kind of create the structure of the car. And it had, because it's not as heavy as a regular car, and it's also not a very big car, but it got 84 miles to the gallon, right? Which is great. And this is not, it wasn't any kind of hybrid or something like that. That was a regular gasoline engine, right? So we can actually do a lot of stuff with it. Now, it looked kind of strange, and so it never went into production. But this was kind of what we call a concept car, right? So this is something that they kind of decided that they could do. And I'm pretty sure that, I mean, the cars that they're building obviously are not all designed exactly like this, but I'm pretty sure that they learned a lot of things about how to create the structure and the kind of the outside of that car that they would be able to then use in their other cars. Wouldn't reduce it by 1/3 of their weight, but you lose a couple kilograms here or there, right? That can really make a difference. And then we can see that other companies are using it. There's a whole bunch of them here. Like, these numbers by now are probably way too old. Probably need to start looking for new results here. But these kind of designs that we just talked about at the time of when we got this number, saved about 650,000 tons of material annually. Right, so this is material that we just didn't use, which was great, because that means we don't have to create all this energy to produce these materials. We don't have to dig them out of the ground, process them, all that kind of stuff. And if it's anything transportation related, also means we don't have to move them around, right? So it could be a big difference. And you can see there's, like, big companies. There's aeronautical companies, Airbus, Lockheed Martin, NASA uses that for some of their designs. There's a whole bunch of car companies. There's farm equipment. Now, how Adidas is using it, I really don't remember. I'd have to go back and check. But the electronics people are using it too, because of course we all want to have lighter and lighter phones. And that was it for today. That's all I have. Are there any questions? then I think I will talk to you on Thursday, but before we go, there's 2 groups that I don't think I've heard from yet about scheduling a meeting, so please do that. I know I'm gonna meet with a group right now. The group that is later on today, if you wanted to hold on for 15 minutes until whatever the end of the class would be, then I'm probably gonna be done with the first group. So if you want to wait, or we can wait, meet at the time that we discussed at 4:45, I think. The other thing that I wanted to say real quick is that there's been a slight change of plans on when I'm going to be in Costa Rica, and that is I'm actually going to be there next week. So starting next week, I'm going to be there. So classes are going to be back in person, back in room 27. So starting next Tuesday. So this week on Thursday, day after tomorrow, we're still online. But after that, we're back in person, and I expect everybody to be there. So no online versions, and please be on time and all that kind of stuff. All right, any questions? All right, then let me stop the recording.